area out there. This is our classroom. We are right here. That is the classroom over there. And it has the heating system labeled here. That hole in the ceiling, right there.
Yeah, so that's where we got our data for the 440 liters per minute. So we talked about this ways of heat transfer. So how we wanted to approach it was now to measure and look at everything that composes this room. The walls, the roof, the windows, the doors. Look at the materials and analyze them to see how good are they as insulators. And this is what we found. So we literally went around and measured the surface area of everything in this room. And we then found their thickness, and we assumed their materials, such as the roof is fiberboard, the floor is linoleum, the doors are wood. So using generalized data, we could find their R values, thermal conductivity, and performing many calculations, we finally found their rate of heat transfer. This is the key data.
Yes, so the rate of heat transfer is how much heat energy is passed through the medium. And so we took data from both inside the classroom and on the other side of each wall. So each wall, each window, we measured inside the ceiling, outside and out in this area here. And we found that the most heat is lost through the fiberboard ceiling. Mainly, a lot of that is because it has a much larger surface area than, let's say, the glass and the doors. But also, it is just we calculate it's a much less insulating material than the exterior walls. So.
Yeah. So to conclude, what we found was, firstly, there's an overcapacity of oxygen airflow through the vent system. So economically, we could actually reduce the amount of oxygen and the levels of air inflow, and still plentiful of air is given to the 17 occupants of a normal science classroom. And secondly, in a material analysis of the insulation in this room, we found that what needs to be replaced or improved is the fiberboard roof and the interior walls. We could replace this with more insulative materials, such as the glass window is actually a very thick layered glass, which is specially designed to be insulated. If we could somehow combine that with and replace the fiberboard with that kind of material, then you would reduce the amount of heat loss and thus better improve the classroom environment.
Alright, I'm going to go ahead and talk about the Hotchkiss heat recovery system, and just to sort of explain what the heat recovery system's purpose is. Basically, in the dining hall, we have large industrial-sized refrigerators that keep our food and whatnot cold, and these refrigerants use a process known as a vapor compression cycle, and I'll get into that later, but basically, as a result of that cycle, copious amounts of heat is rejected through the condenser, and something needs to cool down that heat that is rejected, and basically that is done through the cooling process. Originally, that heat would be rejected into water because water has high specific heat, and that water would be dumped into the sewers. So we were wasting about 5 million gallons of water annually, and just to give you an idea of how much that is, that's enough to fill up the Hickson pool every week for 56 weeks, which is kind of ridiculous. And so that was costing the school a ton of money in sewage bills and water bills, and basically the installation of the heat recovery system made sure that the system was a closed system, meaning that the heat was still rejected into processed water, but that water was going in a closed cycle, so none of it was being dumped into the sewer. We were saving all that water. We're saving 5 million gallons of water a year, which is really great. And could you go to the next slide, please? I'll just sort of get into the physics concepts behind the heat recovery system. So as I mentioned, the refrigeration cycle goes through a vapor compression cycle, which is pretty common with industrial refrigerators. And basically, it's a 4-step cycle. There's the condenser, the compressor, then there's an evaporation and expansion valve. And basically, what I focused on was the condenser, and that's when the refrigerant is changing from a gas state to a liquid state. And as a result, if it changes into a liquid from a gas, it's losing a lot of that heat. Where is that heat going? The heat is going into the process water to ensure that the condenser doesn't overheat. So this is sort of an overview of the circuit of where the process water goes, because once the heat is rejected into the process water, it has to go into a cycle in which step by step that process water is gradually cooled back down to its original temperature, so that heat is being sort of used. And basically you could think of it as recycling heat. So the process water from the condenser comes out top left, it goes down over here into the boiler, and there are 2 steel coils that are stainless steel. So the water and the boiler come into contact through that stainless steel coil. None of the process water touches the boiler water because that would be unsanitary. But basically through conduction, the process water heats the stainless steel coils. The heat travels through the stainless steel coils into the boiler, and the boiling water is therefore heated. And so that excess heat from the condenser is actually used to heat the boiling water, which the dining hall staff uses for dishwashing, other dining hall activities, which is nice because we're actually putting that heat to use as opposed to dumping it into the sewage system. At that point, the water continues, and depending actually on the time of year, it'll either go through a fan system, so when the air is cold in the winter, and in the fall, that air will be used to further cool that process water, so it's losing heat. But in the summer, obviously, the air is not very cold, so there's a heat exchanger, which basically takes the cold water from our cooling system, which is around the golf course. It's pretty far off campus, but that water is used to sort of take some of the heat from the process water and exchange heat. It's pretty self-explanatory. And then that water sort of goes back in to take more heat from the condenser. So it's a continuous cycle of taking heat from the condenser, getting off that heat to other parts of campus where it can be used efficiently, and then returning to the condenser to once again absorb the heat from the refrigerants. So here's the data table. Basically, I was given a diagram, and these are sort of the temperatures at different points in the cycle. And as you can see, there's about a 10-degree Fahrenheit difference between the process water re-entering the cooler at 70 degrees Fahrenheit and the process water absorbing the heat from the condenser at 81.2 degrees Celsius. The process water travels through pipes, which are made from copper and surrounded by fiber insulator. I'll keep it short. But basically, self-explanatory, the fiber insulator is there to ensure that none of the heat in the process water is being lost through conduction or convection. And there are also pressure differences between at different points in the system due to the fact that there are heat differences. And as we talked about sort of earlier in physics, the fact that pressure does have to do with like the kinetic energy of molecules. Hotter sort of water is going to have higher pressure by virtue of its temperature. And then lastly, I'm just going to talk a little bit about chiller lift, and that sort of has to do with thermodynamics a little bit. So chiller lift is sort of the difference in pressure between the condenser and the evaporator in the vapor compression cycle. And if you're to think of the heat recovery system in terms of efficiency, you'd probably say that ideally you'd want the water rejecting heat from the condenser to be more hot so that when it goes to the boiler, it's giving off more heat so that we're benefiting more from the heat that is being rejected by the condenser. But also, it's important to consider that if you cause the refrigerator to reject heat at higher temperatures, that's going to cause a greater difference in pressure, which corresponds to sort of more energy needed to be done by the refrigerator through its compressor, which is another part of the refrigeration cycle. So there is sort of that idea of balancing between heat efficiency and power consumption of the refrigerator. And I'll just quickly show you sort of like a classic thermodynamic diagram. One is rejecting heat at a higher temperature than the other. You can see the pressure difference is as a result greater, and therefore the compressor in the refrigerator has to do more to equalize the pressure between the higher pressure and the lower pressures. And this is sort of a power graph for power consumption. The blue line indicates the power consumption for a pressure differential of 20 psi as opposed to the green, which accounts for a pressure differential of 10 psi. And that's pretty much all I'm going to talk about.
Okay, there's one question.
My question was about forces. You were talking about the liquid that's in that cycle and how helpful it is that it's not just going straight to the sewage.
Yeah.
Is there like any time or place where that can become deteriorated and not be useful?
Not as far as I'm aware. The water is maintained. And sanitation is not an issue because that water is never touching the boiler water or anything we're eating or drinking. So.
Thank you.